Alright, so the last thing we have to talk about with geometric sequences is their sums when you add them together, just like we talked about with algebraic sequences. Or, I'm sorry, arithmetic sequences. And so what happens is, if you're going to add up the first n terms, okay, that would be notationally the sum n equal 1, oh, I'm sorry, sum k equal 1 to n of a sub k. If you were to do that, essentially what you're doing is you're taking each term, because it can be written in terms of the original a sub 1, you can do a substitution, a repeated substitution. So as you're adding these in, you got a sub 1 plus a sub 2 plus a sub 3 plus dot 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 up to a sub n. That's what this notation means, right? Plug in the 1 through the n. Now each of these, like a sub 2 is really a sub 1 times r, and a sub 2, oh, this should be a sub 3, my bad. A sub 3 should really be a sub 1 times r squared. And then you get r to the third, r to the fourth. This would be r to the n minus 1. Okay. And so if you do all those substituting, you do some arithmetic with, or some algebra with it, simplify, then the formula that you will come up with will be this. S sub n equals a sub 1 times a really weird fraction. The fraction has 1 minus r to the n on top and 1 minus r on the bottom. Okay. So let's just try this. I'm not going to go through the details of how this works out. The details are spelled out in your textbook. But again, it's just this repeated substitution and then a bunch of algebra to simplify it. And so we'll try it out with an example. Let's try to find the sum of the first 10 terms of this sequence. Let's go. Oh, let's define. Actually, let's define it recursively rather than doing it this way. Let's define it recursively. I'll just start listing out some of these. Let's do like a sub 1 is. I'm trying to make this up as I go. Let's start with the number 4. And then let's cut it in half. So 4, then 2, then 1, then 1/2, and so on. Okay? So this is a geometric sequence. The a sub 1 value is 4. The r value is 1/2. You're repeatedly multiplying by a half. What you might notice, I hadn't mentioned this before, but what you might notice is that these geometric sequences are similar to the exponential functions we've talked about before. You know, maybe where you're cutting it in half repeatedly, or multiplying it by a factor like 5 over and over again. Okay, so here's our initial term, here's our common ratio. The other thing we need out of this, let's see, a sub 1, r, and then we need n. Well, we know what n is, it's the 10th one. Okay, so it pretty much gets us everything, n equals 10. So if I wanted to find the sum of the 10 terms, I don't need to write out all 10 terms or add them together. If I follow this formula, s sub 10 is equal to a sub 1, which is 4, multiplied by 1 minus r to the n. Well, r is 1/2, n is 10, so it's 1/2 to the 10th power, divided by 1 minus r, which is 1/2. Okay. Now if I go through and simplify this, it is a little bit ugly. First of all, 1/2 to the 10th power, well, 2 to the 10th is 1024. And so this is 1 minus 1 over 1024. And on the bottom, it's just 1 minus 1/2 is 1/2. Right? And so now we got 1 minus 1024. Well, if you think about it, I'm sorry, 1 minus 1 over 1024. If you think about it, this 1 is really just 1024 over 1024, common denominator. Subtract this 1, you get 1023 over 1024. So I'll write that out. It's 4 times 1023 over 1024 all over 1/2. Well, remember, dividing by a fraction, you're going to do a copy dot flip. So 4 times 1023 over 1024 times 2 over 1, right? Divide by 1/2, same as multiply by 2 over 1. I'm going to do a quick canceling here. I know that 2 goes into 1024, it'd be what, 512 times? And then 4 goes into 512 128 times. So that becomes 128. And so really what I'm left with is, let's see, 1023 over 128. That's it. That would be our answer. Now I could always turn that into a reduced fraction. That may actually be reduced because I think they don't share a common factor. Oh, yep, that's it. And so that's approximately, if you rounded it off, 7.99 with a bunch of other decimals. Okay. And so that is the sum of these first 10 digits. Again, we don't have to go through and calculate all 10 of them. We can use this formula then to find the final answer. Okay. Now the last example I want to show you is what happens if you add an infinite number of terms together. It seems kind of weird to be able to do that, but with geometric sequences you can, so long as the r value is less than 1. Kind of like in our case here, we had an r value of 1/2. And in that case, you know, you're decreasing every time you go out. There's some more theory behind when this works. I won't get into all those details. But essentially, as long as that r value is less than 1, you can make this work out for an infinite number of terms. Think about that. So that's a lot of terms. Let's go through this same process. Now, the formula is different. The formula for an infinite number of terms, and we couldn't do this for arithmetic sequences, it only works for geometric. The formula for an infinite number of terms, oh shoot, I was going to write s sub 10. We'll just call it s for an infinite number of terms. Of course, it would be k equal 1 to infinity of a sub k. That sum ends up being a sub 1 over 1 minus r. It's a very, very basic, simple fraction to plug stuff into. And it's a really cool formula. I won't go through the derivation of it, but again, it kind of comes from this repeated application of plugging in consecutive terms and the formula. So Anyway, this ends up being the formula when we're all said and done. These are called geometric series. An infinite sum is called a series. Infinite sum is a series. Okay. So a geometric series. So let's just take this previous example and let's say we run that out infinitely far. You have an infinite number of terms. Okay, well in that case, the a sub 1 is 4. The r value was a half, so it's 1 minus 1 half. And 4 over, well, 1 minus a half is a half. You do the copy dot flip again, so it's 4 times 2 over 1, which is 8. Now that makes sense to me because when we did this out to 10 terms, we got 7.99, which is close. 10's a lot of terms. If you did 100 terms, you'd get even closer to 8. It'd be like 7.99999. I don't know, something like that. And so the farther you go, the more terms you get, the closer you're going to get to 8. But 8 is the sort of the limit, the max. It's as high as it goes. Can't go higher than that because here we've gotten all infinitely many terms added together. Okay. Again, just this formula is very simple to plug stuff into. And I guess that's really the last thing I wanted to talk about with geometric sequences. So, hope you guys all enjoyed your Easter, and looking forward to the end of the semester coming up pretty quick here. So we got some tests coming up, and make sure that you do check e-learning. I have a new schedule posted. Also make sure to check my math lab because I'm going to have more assignments posted, and including some test reviews. So keep an eye out for those. Right? Thank you very much.